the audio should be fine. And I'm waiting for someone to connect. Still have 0 concurrent viewer, 1 concurrent viewer. Just 1. Grab a glass of water and then waiting for some more to appear. I have 3. Well, 3 is a good number. So 4. It's like amazing. So welcome to the more or less the semi-last lesson on probabilistic robotics. And today we will be introduce some navigation concepts for mobile robots, and also we will bring up navigation system, so like basically our own navigation system, so you will be able to do maps and to do stuff like the one you have seen me doing in the class, the map and so on. All right, so small taxonomy of navigation, right? No. Huh? What's going on? No data? Good. Hope you still see me. Ah, better. All right. Go here. Close. All right. So outline of the lesson, we leave it there. Let's start from something you have already seen. So what I want to do is to introduce you some concepts that allow you to design a system that will be able to drive a robot from A to B while staying localized in a known map. So the navigation issue is nothing else than an instance of the famous sense plan act architecture that you might have seen, might have encountered in artificial intelligence. So basically we are treating our robot as if it was an agent, and this agent technically is instructed to bring the word or the configuration of the word that he has internally into a desired configuration. Now, in the case of navigation, the desired configuration is the robot has to be in a certain location, which is the goal location. Okay? Like now, to move to this desired location, the robot should understand the environment and understand in particular what? In particular, it should understand the where it is actually positioned in the environment. So if I want to go to the living room, in order to go to the kitchen, the very first thing that I need to do is to figure out where I am. Okay, so like assuming that I am now in the study and I want to go to the kitchen, which is in the other room, if someone tells me go to the kitchen, well, in order to plan the path and to plan the sequence of actions that would drive me from the study to the kitchen, I need first to understand that I am in the kitchen. Okay, and this is not something that I get for free in the specification of the task, because the task simply tells me go there from wherever you are. So I need to somehow understand enough of my surrounding, or understand estimate my state. In this case, the state of the robot might be just its location in the environment, in order to plan the sequence of actions that would bring the perceived state to match with the desired state. Okay, this is kind of standard. And in order to do that, a robot needs to also possess an additional information, which is crucial to navigation, which is the map. Because without having a map, I cannot tell where you are, right? It would be meaningless for me to tell you go to the kitchen if I don't have, if I don't know where the kitchen is. And it would be also impossible to figure out that I am in the study if I don't know where is the study and how the study looks. Okay? Now, this talk is about basically the taxonomy of navigation. So, in this domain, it is normal to talk about quantities and about process that are used to estimate these quantities. Now, the quantities that we are interested in the task of navigation are three. The first quantity is the map, how the environment looks like. So this is the first quantity. The second quantity that I'm interested in, the second element, variable of my potential state, is the position of the agent of the robot in the environment. Okay, and then there is a third quantity which is desired, which is relevant to carry on a navigation task, which is where do I have to go? Okay, and in addition to that, also the path, the sequence of locations that I need to traverse in order to move from where I am to where I want to be. Now, assuming that and in all this estimation process, what it's not assumed to be known, but what you can rely on is the fact that the robot constantly perceives its surroundings through its sensors. Let it be a laser scanner, let it be a camera, or whatever you want. Some other sensor that is able to perceive its surroundings. Now, if you have questions, please feel free of write in the chat. Now, let's address the simpler. So three are the quantities. Okay, so we have the map on the one hand, we have the robot position on the other hand, and we have the path and the desired location on the other hand. Now, each of these three problems might be interesting on its own. So estimating each of these three quantities might be interesting on its own. Because sometimes you're not even interested in driving a robot, because someone might ask you to construct a tool, a trailer or whatever, that it's able to always localize itself. Imagine you are in a supermarket and some very rich guy says, people are so I'm interested to know the distribution of the trolleys, i carrelli, the trolleys in my supermarket, and I want to know where each of these trolleys. In this case, you're not interested in driving the trolley, but you need for sure to understand where the trolley is. Okay, and then you might implement some sort of localization for these trolleys. Maybe you can sensorize the wheels and you can mount something on it, possibly cheap, like I don't know, UVB, ultra wideband receiver, or an RFID receiver that localizes based on the products that it senses, and so on and so forth. Like like when you pass to the casa of the supermarket, there is this thing that removes the stolen tag from the product, and so that it doesn't beep beep when you pass through the doors. Well, and then in this case, you could rely on this on the distribution of the goods in the supermarket to have some sort of location on where you are. This could be an example. Of course, the objects shouldn't be moving that much, and you don't need to have an evil that moves the goods from one side or the other. So on the trolley, you mount one of these devices that are able to read the RFID tags, and the RFID tags are on the products, and based on that, you could figure out roughly where you are in the supermarket. so to say. But then in that we have defined also what is localization. So localization is the task of estimating the robot position in an environment, given the map, because in our simplistic task of a trolley moving in the environment, the map was given externally, so it's treated as a constant. So if you have a map and you have a bunch of sensors mounted on a robot, and the task you required to answer, or the goal you have to accomplish is to estimate my position given a sequence of measurements, and to track it over time, then we are talking about localization. Hope it's clear. So localization means I know the robot position, I know the map, I know the sensor readings, and I'm interested in estimating the location of myself in the environment. Then there is another task that you might be interested in, which is in the end, which results in another variable, which is I'm interested in constructing the map, assuming that there is a little external station that is capable to measure my location. So imagine now in this scenario of the trolley in the supermarket, which is localizing based on the distribution, based on the tags of the goods that are put in the environment. Well, it would be rather impractical for me to map or to determine the location, to annotate on paper and then on a data structure that can be used then by the robot the position of every of the goods, also because the good might change and so on. So I might say, you know what, I buy a special device that resolves automatically the localization problem, or at least that is able to accurately estimate the position of the trolley in the environment. Let it be that I buy a special GPS, indoor GPS, which is able, through its antennas, through its ensemble of appliances, can tell me where the trolley is. There are UVB systems for indoor that do these sort of things, ultra wideband, that basically there are systems that are able to triangulate or to trilaterate the position of an object, of a beacon, from a set of antennas which are located in the environment at known position. So if I know exactly where my trolley is in my, let's say, reference system of my positioning GPS, what I could do is to move the trolley in the environment slowly, and then try to sense all the location of these RFID tags, and then whenever I sense a tag, I just put it with respect to me where it is in the map, right? And at the end, what I would have is basically the constellation of RFID tags per location. Of course, you can do also some denoising in this case, because you are sensing a tag from multiple directions, and so in case the single measurement is noisy, you could do some sort of averaging of these measures in order to more precisely localize the tag. The outcome of this process, where you assume to have a perfect location or a reliable location of your position, and you record the sensor data, and your goal is to estimate ultimately the map of the object, is said mapping. Okay, so I have a perfect estimate of myself. I just go around, I sense the things, and I want to construct a map. Mapping was nothing else than the exercise that I proposed you last time, where I've given you a data set, a bag, which contained the path of a robot according to the odometry and the laser scans, and what I was asking you is to put these points in the odometry reference frame based on the transforms you were reading. So mapping might be also a simple task if you don't want to, if the sensor is easy, like a laser scan. Right? Then there is a third task, which is like the most commonly used and often is confused with mapping, which is SLAM. SLAM is a little bit more complicated problem, because of the because it relaxes the assumption that you know the robot location in mapping. So they both have the same goal, or better, SLAM stands for simultaneous localization and mapping, I already said. And as the name says, as the goal of estimating both the map and the robot position or the robot trajectory in the environment, only starting from sensor readings, right? And then we will see also an instance today. Now, why doing SLAM instead of mapping? Well, because you don't always want to buy a special GPS. Why do I do SLAM at all if I have the floor plan of the building because I've constructed that building? Well, because the floor plan of the building only senses aspects that don't necessarily can be determined by the robot itself. For instance, if the robot has a camera, it does nothing with and you want to use the camera to localize the robot in the system, it does nothing in the it doesn't carry any special information because they sense two different cues of the environment. And then there is a third problem, which is path planning, which actually you have all the means to solve if you have done at least a star, right? Or if you have done some planning algorithm that constitutes in calculating the sequence of robot locations that would bring you from where you are, and to where you want to be. Now, in order to resolve path planning, you need to possess at least the information of where you are, because otherwise you don't know where you can, from where to plan the path. And also you need to have the map, because you don't want to plane a straight line, a path which is a straight line that goes through the walls. And of course, by enabling and disabling all these quantities in the estimation process, you get all sort of hybrid configuration of or hybrid mixed tasks. Like, for instance, if you assume that you have a perfect GPS and you are interested in automatically exploring the environment, but you need to have a perfect estimate of your location, then we are talking about exploration. In exploration, your robot decides where to go in order to maximize the coverage of the environment in the minimal time. And in order to do so, it relies on an external positioning device. In contrast, there is another class of problems, which is assuming I have the map and I need to go from A to B, but in going from A to B, I need to, so to say, be always localized. I make you an example. Imagine you have a tiny little boat and you're not an expert of navigation, of moving in the sea, and you want to go, let's say, from Civitavecchia to Genoa, right? Now, from Civitavecchia to Genoa, if you would have a GPS or something, you just could take a straight line. Genoa is in the top part of there is a curve. Here is Genoa, for those that are not Italian. Here is Genoa, here is Civitavecchia, and then in order to go straight, you would have to go this way. The problem is that you have this tiny little boat, and then you don't want to go in the open sea, because once you are in the open sea, if you're not able to read the stars, you don't know where to go. So in this case, your interest would be to go to Genoa, yes, but while staying always localized. And so you would do like the ancient people that were doing coastal navigation. So they were always navigating not too far from the coast, so that they always knew that they could go back to a they were keeping themselves always localized. They always knew also that they could go back on ground, right? Now, let's talk about the quantities that we want to estimate, that we have, or that we are interested in, that we have said they are three: the map, the robot location, and the path of the robot. And given that we are computer scientists, and in the end everything else has to be dealt with a program, let's talk about potential ways how we can represent a map. The map representation depends on the sensors that you have mounted on the robot, and in general, it's a flexible data structure that should just like contain enough information for the robot to accomplish a task. So if you are interested, for instance, in a robot that moves in a supermarket or that moves in a hospital, you might also want to know in the map which patient is in every room, paradoxically, right? Because in this way you could instruct the robot, hey, go to patients XY, right? So you add this information to the map. But from the point of view of navigation, the map should contain at least some data that could be matched against the sensor data in order to determine your position. There are classical, and this also depends on the traits, on the features, on the characteristic of the entire navigation system that you have. Classical way of maps that we will be seeing in 2D, but you can also imagine them in 3D, are occupancy grids, which are just grids, matrices, images, where the color of a cell denotes the probability that this cell is occupied. So we would have darker cell on the walls or on the intersect. It's white cells because there's a low occupancy probability in locations when the robot is supposed to be able to walk, and the gray cells where there is no information about what's inside. Okay, and this is the most simple map and most intuitive that you can encounter. The only parameter that you have in such a map is basically the cell size, the dimension of how much a pixel in your image should be when you go in meters in an environmental quantity. Then there is another class of map which is suitable for localization only, which is the landmark-based maps. Now, you could nicely localize into a map of this sort if you would have a laser scanner, because you would be able to sense the impact point of the laser beam on the walls. But what you would not be able to do so easily is to localize if you have, for instance, a map, a camera. Now, if you have a camera, well, you can't do much with it. But what you could do is to in the simplest case, you could structure your environment, and you could, for instance, mount a bunch of QR codes on the walls of your environment, and then each of these QR code would act as a unique element in the environment that could be detected by some sort of homography estimator that is mounted on the camera, and then it tells you what is this, that this QR code is the QR code number 3. Now, in order to localize in this environment, how would you represent the map? Well, the map would be nothing else than the position of and the ID of each of the QR codes in the environment. Okay, and then we are talking about a landmark-based map, and then you can also have more articulated representations like hierarchical representations, where you organize your map in a graph and you attach because the map might be huge, and so you don't want to have a lot of information in your system every time, but you just like that want to download parts of the map which are relevant for you. But in order to download the parts of the map that are relevant for you, you need to know more or less how they are organized in space, and so you could organize these portions of map into a graph that where each node is a submap, and there is an arc between two submaps. For instance, if you can go from one submap to the other submap, and you could also use this structure for doing path planning. Now, you could have a hierarchical path planning. Now, other two quantities which you're interested in is the robot pose and the path. Now, in this course, we will deal with 2D problems, not with the 3D problems. But the situation could be extended easily, conceptually easily also to 3D. Now, the robot pose typically is defined, and the robot pose is nothing else than a position, a translation and orientation in the space. But in which reference frame the robot pose is defined? Well, it's defined in the reference frame of the map, because when you say the robot is in 1010 pi half, you're saying just a number, but this number has no meaning if you don't fix a reference frame for on which this 10, 10, and pi half has to be measured. Okay, so the robot pose is defined in the reference frame of the map. The path, in contrast, is typically two things. The path is a sequence of waypoints, so which is a sequence of robot position and orientations that the robot has to take in sequence in order to reach a desired location. Normally, the current planning systems, they operate at multiple, let's say, resolutions. Then you have a global planner, which is fast, that produces a coarse set of locations for the robot to go from A to B. And then, it's like for me, someone telling me, I go from where you are now to the Colosseum. All right, no, it's not that I'm planning every single action I'm doing to go to the Colosseum. I have a rough idea of where the Colosseum is, and I know that first I have to exit my building, then I have to walk through Maranella, then take the Casilina, and then take the train, and so on and so forth, right? So I have macro states, and then each of these macro states gets then decomposed in some macro commands. Each of these macro goal is then decomposed in smaller goals, like for instance the action of exiting my house might be decomposed in the task of exiting my house. So to reach that desired goal might be decomposed in all a set of actions for which I actually need visual feedback, because I need to know how to put my steps one after the other in order to walk through the door. And ultimately, all these sequence of state through a hierarchy of tinier and tinier planning algorithms or control algorithms boil down to actions that can be issued to the actuators of your robot. Now, here you see, and we will run it, we see an example of the localization problem, whose goal is here shouted loud. So the goal of localization is to determine the robot position, assuming that the sensor readings are coming in sequence. What we see here is an example of localization. At the beginning, each of these dots represent the robot position. The robot starts moving, and after a while that it moves, it has accumulated enough information to disambiguate its location. And then from this point on, you can see the blue dots is the scan, which is overlaid to the map. Once it moves, well, it stays localized. At the beginning, all the particles, all the dots were spread, denoting basically a uniform distribution, like you didn't know where you were, you could be in every possible place, but as long as you move and as you gather information, you get better and better. And then once you localize, either you stay localized or you might get lost if there is some evil that takes you from one location, that kidnaps you, technically. Path planning. Now here you're seeing another example of path planning with an old robot of the good old Freiburg times. Imagine that during all this process, the platform has to keep localized, right? Like once you say to the car or to your robot to go from A to B, well, it has always, during the execution of the task, know where it is. And what we see here is like an interesting rendering, because this is the view of that the robot has about himself, where it is, and this is the location of the robot in the environment, in the true environment. And so you could notice that the robot stays localized. What we see here is like the path, or we have several paths. We can see that the robot here was instructed to go to this location, so it was a 3D planning problem, so it had to go under the underpass, climb up, and climb over here. Now, in this case, the path was represented as a sequence of cells on a surface. Like there is a traversable surface. Imagine that the surfaces can also take a surface can also go on top of each other, and then it was able to plan a path basically in 2D, only that the surface was not just a plane, but it was it had a z offset. And of course, to carry on this problem, there's all sorts of things that have to be carried on. Mapping, I've already stated in the initial slide what the problem is. Basically, I have a perfect ego estimate of the position of the robot, and what I'm interested in is to construct a map that I can localize in. Problem is that typically you don't have a perfect estimate of the robot position, and so we have to resort to solve SLAM. SLAM stands, as I said, for simultaneous localization and mapping, and basically is the process of estimating concurrently the map of the robot and the trajectory of the robot in the map by processing the measurement in sequence. And this is what is typically done at least once by robotic systems. It's a little bit more complicated, or substantially more complicated than pure mapping or pure localization, because, if you estimate a bad map, then you're also going to get lost in the environment. And if in order to estimate a good map, you need to have a very good trajectory. But if the trajectory is bad, then also the map becomes bad. If the map becomes bad, your estimate of the trajectory is going to be bad because you're localizing on a wrong map, and then the system basically blasts. Now, this is an example of SLAM in action. You will run it on your machine. Here you see basically a graph-based SLAM system that is going on. So you can imagine that this robot is constructing a graph as long as it moves. It deploys nodes of a graph, and then at every point in time the robot is adjusting the current laser scan with respect to the previous one in order to estimate its position by means of a scan matching algorithm or an ICP like the one that you have seen in one exercise. And then, of course, this leads to some sort of drift accumulated by the platform while it moves, because I'm only correcting with respect to a previous location, and if the previous location is a little bit wrong, also the next location can be better. But what you can do is to exploit the revisit actions, like when you come back from a long path, when you travel for a long time in the unknown, and then at a certain point you go back to a known location. If you identify this known location as such, you could try to relocalize with respect to this known location, as it is happening here, and by doing so, you can refine your entire trajectory onto the path. Okay. Now, we have seen basically what are the variables involved, and we have seen what are the three main problems that we will address. And now, what do we need to navigate a robot in ROS? Of course, in this course, I can't ask you to construct navigation problems and these modules, because you don't yet have the knowledge or the experience to do these sort of things. But if you are interested, there is probabilistic robotics, where we will definitely dive into localization and SLAM. But you can get sensible by using these systems made by others, and to figure out what they really need to do and to understand how to operate, and how to build on top of these modules. Now let's think for a second, what is the minimal set of things that we need to navigate a robot? But really the bare minimum. The bare minimal is definitely a map, which shouldn't be constructed online or whatever. You can take all the time you want to construct this map. It can also be made by a human being or whatever, or it can be recorded by the robot and then manually adjusted and fixed and massaged by a human operator. I mean, it doesn't matter. You need a map anyway, and it's a concept of your problem. Oops, this is Roomba speaking about maps. It's synchronized with the lesson. You need a map. You need a localization module, because in order to go from A to B, you need to be localized all the times while you go from A to B. And also you need a path planning module, because in order to reach a location, you need to know the sequence of actions that you have to take for going to the desired position. Now, if you work in a static environment where there is nothing else that moves, and you're guaranteed that the map will be the same, will be never changed, then you're fine with these minimal components, and I strongly unadvise you to add more. But the problem typically is that there might be errors in the localization, there might be errors in the planning, and in particular the environment typically is not static. So that not being static means that you might have people around, you might have passages appearing and disappearing, like people. You might have noisy estimates, because maybe your localization is not yet converged, as in the video that we have seen before. It takes a while before determining where the robot is. So like normally you add to your platform some additional components. The most important of them is obstacle detection, because if there is one property that you want to be accomplished by your robot, is not to bump into things, right? So you need to have a module that runs at a higher priority with respect to path planning, with respect to the control, that that determines if there is going to be a collision. In case there is going to be a collision, stops the system and takes some recovery actions. Then maybe you might be interested in adding some sort of in populating or in altering your map by adding the objects that you're currently seeing. So you might have that the robot moves in this environment, and then albeit there is an open passage. After passing in front of it 3-4 times, it figures out that the passage is closed. A little bit of what's happening in Rome every time you go to a street and then you find that these orange things. Now, after 2 times you pass to these orange things, then you have to put this obstacle in your map, so that the next time you will not traverse, you will not try to enter in a street that is in the end closed, right? And then, in particular in the city, the orange things are always put and never taken away, right? This is the message. So we have a decreasing number of streets available. Okay. So these are the components that you need at minimum: a map, a localization module, a path planning module. And in addition, we might want to have also some obstacle detection or avoidance module. So now each of these tasks is carried on typically by a program or a ROS node that takes a specific information and produces a specific information. Now, you might have noticed that in the previous slide I was stressing on the fact that the map, or the main map, at least during the navigation task, stays constant, right? And not only, you might have noticed that the map is typically used by more than one, for accomplishing more than one task. In particular, this task is localization, and another task is path planning, right? Now, it might make sense to imagine that you have a fleet of 150 robots that are moving in a building. It might make sense, instead of loading physically the map from a file on the robots, it might make sense to have a global server in your environment that stores the more up-to-date map. In case, in this way, if there is a change in the map, you could broadcast this change in the map to every other user, right? And this is implemented by the navigation stack of ROS and my navigation stack by introducing the node of a map server. The map server is nothing else than a node that implements a service that has only one or has 2 functions: put map, if someone wants to publish to everyone interested specific map, or get map. Okay, get map receives the map. So map server is a simplistic program that loads the map from a disk in a certain format and makes it available to everyone else. So it's somewhere there. Now, and that's it. What the map server provides is a thing which is called map. topic, and the topic would be of type grid map, because ROS is, so we're talking about the 2D navigation stack. And there is another object which is interesting, which is AMCL, which is the localizer. Now, I have the facility for producing the map, and now I need to localize into it. To localize into it, what do I need? Well, to implement a trivial localization that is, how to say, that is entailed to operate with laser scanners, you could use the module in ROS, which is called Adaptive Monte Carlo Localization, or you could use mine, that you will see later, which they basically implement the same things, but mine is much faster. What does this module needs? Well, this module needs the following things. The very first thing that it needs is an estimate of the odometry. So how much my mobile base is moving according to the encoders, because this is an information which is always available and it would be stupid not to use it. Another information that it needs typically is the laser scans, because it's made so in order to localize, it uses the current laser scan to match it against the map. And another thing which is super important is it needs to know where the laser scanner is located onto my platform, right? Because if I don't know where the laser scanner is located into my platform, well, I don't know how to determine whether I'm moving forward or backward. So it needs to register to the transforms, okay? Okay, and then there is this big blob over here, which is called move base. Move base, and what is the localizer producing? Well, it produces basically a transform. Which transform? It's a transform that logically maps, expresses the position of the robot based on the information that it receives with respect to the reference frame of the map. Okay? Now, think about the mess that it's. Okay, we will go back to this in a second, because I might need to draw a transform tree. But for a second, imagine about the transforms that we have in the game. We have a reference frame, which is the map, which is giving us basically the origin of the map. We have a odometry that has its own reference frame. The odometry is this process of integrating the robot position that starts in 000 when the robot, when you turn on the robot. Now, given that you can turn on the robot in every position of the map, the odometry always starts from 000, and there is no relation between the odometry reference frame and the map reference frame. And then also what we have seen from the transform tree that we have investigated last time is that the odometry reference frame is the one, there is a transform from the odometry reference frame to the base link reference frame, or the base footprint reference frame, which means that we are able to tell the location of the robot, where the robot moved since when we turned it on. Okay, and then on the base link everything else is mounted. Now, the localization program could produce an information about position in the form of a transform by simply broadcasting a transform that expresses the position of base link, which is or base footprint, which is the center of the robot, with respect to the reference frame of the map. But by doing so, we would have two independent branches of the tree, because we would have, on the one hand, this is the base link. On the one hand, we would have the odometry reference frame and the transform odometry base link. On the other hand, we would have map reference frame and the transform map base link, right? And then on top of it, we would have, or on the bottom of it, we would have all the rest of the tree. So this is, one might say this is still a tree because you don't have loops, and I agree with that, but those that designed the TF system, they expected that there is some sort of ordering in the nodes. So this wouldn't work. In contrast, what you could do to fix the situation is to modify slightly the expression of to determine the transformation that that is between the odometry reference frame and the map reference frame. If I would know this transform over here, then I would be able to express the very same information by saying the position of the odometry origin with respect to the map. So basically, by guaranteeing this that this chain of transform is closed, you could say where the robot is by formulating a very simple transform equation where you say the robot pose in the map should be equal to the robot pose of the robot with respect to the odometry, which is the robot pose of the odometry with respect to the map, which is multiplied with respect to the robot pose of the robot in the odometry. So like I will just write it down because it's easier. And now that I am at home, I can also write, guys. It's amazing. Oh, it's not working. Okay, maybe you can see something. Okay. Yes, you can see something. Now, I have a reference frame, which is base link. And use this. And then we have odom. And we have map. I think you see. Okay? And then this would come from the localizer and this would come from the robot. Now, the problem is that then here I have the rest of the tree, which I don't want to have. What I could do instead is to make the localizer to send this transform over here in a way that by sending this transform, this kinematic chain is preserved. Okay, so namely, I could write T robot, T map robot should be equal to map robot should be equal to T map odom times T odom base link or robot. You could write something like that, right? Like you could publish a transform that moves from here to here in a way that this transform here doesn't change. So then you don't publish anymore this link, you publish only this link, and then you live with that. And then you have once again a straight kinematic tree. So like now my question is like, how much is this transform over here? Well, you can simply multiply both of these equations by the inverse of this to the left, and then you get the transform of the map with respect to the odometry, or the odometry with respect to the map. Okay? That's the message, and that's what the localizer does. Now, like, become smaller again. And I turn off the light. It's raining a lot. I think you appreciate not being in San Pietro in Vincoli today. All right, let's move on. Now, there's a gazillion of, I hope you got sensible on why the odometry, why the mapper, so the localizer produces this transform. Also because by doing so, you might have that the system runs at different frequencies. For instance, you have if you have a very lousy machine, you might have that the localization sends an estimate every I don't know, 2 seconds, and you might have that the odometry runs at 100 Hertz. By doing so and integrating them into the transform tree, you might have a more continuous estimate. Okay, and in general, you don't need to run the localization so compulsively, no, like let's say 10 Hertz, 5 Hertz, it's more than enough, even less. Now, building a map. There's many ways of building a map. If you follow a navigation tutorial on ROS, you will find out how to use gmapping. Now, I am basically the daddy of gmapping when it's part of my PhD thesis long ago. But I mean, there are also better things that you can do. But in order to use a mapping tool, what you can do nowadays is to record a bag that contains ODOM, scan, and transform. You drive the robot around. Recording a bag means registering to ROSBag record a data stream from the robot that you joystick around, and then you pass this recorded data to gmapping or to your mapping system, and it will construct a map. The map will be then output as an image that shows the blueprint of the environment, as you have seen already, and also a configuration file that tells you how big is the map, the origin, the size of the pixels, and so on. Now, the traditional way of using, if you follow the tutorial on Navigation Stack, you will find also that you can bring up Navigation Stack using AMCL, and this algorithm is basically a particle filter, which is a program or an algorithm that estimates a probability distribution over potential locations of the robot given the sensor measurement that you have, and it represents this probability distribution as a set of hypotheses, a set of particles in the environment. The localization by tradition outputs this base footprint, the transform between the map and the odometry that makes the transform of the base link in the map consistent, as I said before. Now, for setting up the ROS navigation stack, you can do this, right? Or you can do better, because now I'll present our say ecosystem for navigation, and I'll tell you how to build. No, normally, like if you look in the repository and also follow up the email of Omar, you will find the instructions on how to build this repository. I'd like to know if someone of you has already built. Please write on the chat. Now, to build this workspace, this thingy, what we need to do, beside installing some software, very first thing we need to do is to initialize the workspace. It's a ROS workspace. And then we build it. But given that I'm running OBS, I will restrain only to 4 cores. And then we wait for some time. Now, it will take some time, and now all the people that have installed the virtual machine will suffer a bit, the others will suffer less. Please, 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 don't give more than, don't give less than 4 gigabytes to your virtual machine if you have one, because it's not going to compile. And in case the compilation fails because you get a compiler error, then decrease the number of cores. Compiler error meant as internal compiler error or out of memory. And now you understand why the build system. Okay. Adriano said yes. Well, we will do everything in steps. Now I'm building. Let the machine build, and we go on with the slides. Now, let me say what you have in this package. I repeat, this is our software that we are using in our research and so on. But I mean, namely, our modules are designed as classes, right? That's it. And in order to avoid building a million and a trillion of main programs that do nothing else than calling a function of a class, we blasted this aspect, and we have a system which is a class loader, which you can tell him the libraries to import, so to say, as a sort of command line, and then you can compose these modules, these blocks, as you want in order to implement your system. Once you have it, you could also run the pipeline that you have constructed. After the build will be finished, which will take, let's see, how long it will be taking. It will be taking, it will be taking a bit because I cropped the course. Yeah, now it's building and there's not much I can show. Then we have a configuration editor that it's a program to graphically construct these pipelines. And also we have a convenient program which is outside of the ecosystem that allows you to control a machine through the web server, through the web, by logging into a very specific address onto the remote machine. Of course, in this case, this program here, we will see it better. This program needs to be, each of these programs needs some sort of configuration file because they are generic and they don't know what to do. Now, 5. Oh. Ecosystem. We were here. Okay. Now I think I'll need to wait for the build to be over. So there's not much I can do. If you have questions, I'm gonna take them. It takes time. It takes time. If you have questions, I'm gonna take them. But meanwhile that it is compiling, I can also tell you that there is a configuration game that you have to go. Now in this folder there is a file which is named dl.conf. We have to edit this file which is called dl.conf to match, there is a string here, this is the path. This dl.conf is a file that is read by every program in the pool, and that specifies what are the libraries that it should load, okay, at the beginning. So we postponed it. No, you can use, Antonio, you can use any editor you want. Emacs is only for me. Antonio asked, is it possible to use Sublime instead of Emacs? You can use any editor you want, but if I will ever have to touch your machine, be sure that Emacs is installed. Because I'm handicapped on it with every other editor. That's the reason. So it's my limitation. What I was saying is you have to edit this file, and then here there is a path. We have to specify this path. This is the expansion variable, so it's my home, so that it matches what? It matches devel. So you have your workspace, wherever you have downloaded it, then there is devel and there is lib. So this is the devel lib directory of the directory where I launched, where I started Catkin build. So if you look at the beginning, when I started Catkin build, I was into, well, I was here, right? So in the workspace, okay, this should be the top level directory of the workspace. So what we need to do is here, pvd, to be sure that this path here is put into this variable. So either I do this, okay? It's a very long path, but okay, instead of putting home PR, I could say the expansion of the home variable. Okay? And then you have specified where is the path where the loader has to load the objects. Okay? This is the very first thing that you need to do while it compiles. So, of course, clearly you might have this folder, this initial part different, right? You have to adjust it so that it matches the path. Or here you can also put home PR. Oh, this too. The global path. And then the rest is given. Okay? Now it's building, it's building, it's building. Building, building, building. Did it build? Oh, it looks like it built or not. Huh? Maybe it has built. I've lost it. Huh? No, it was here. Yeah, 18/26. But meanwhile, remember what you have to do to edit this DL config file, because this DL config file will be the one that will be responsible of load, will tell the system where to load the modules. Okay. Then another aspect that another thing that I recommend you to do is to add to your bin directory two programs which are compiled by the system. These two programs are devel lib srg2 executor srg2 shell. The shell, okay, well, it requires raw score. You have always to launch this evil unless you. This is the shell. Okay, so remember, this is a binary C program that is also, you can also start with run. So there is this binary here, and I'd recommend to put you this binary into the shell, or to do as I do, to add a symbolic link into the bin directory of your own. This is the first binary that I'd like you to have available, and the second binary will be this. This is the node editor, which is a program that allows you to add components and construct your pipeline, right? Whatever you can do. Then you can create arrows, you can connect them. Of course, this wouldn't work because these two modules are incompatible. Okay? This is a second program that you can install. So let me repeat them. srg2 shell within the package srg2 executor, and appnode editor within the package srg2 config visualizer. Okay, remember these two programs. Now what I'm gonna do for my decency is to Emacs to edit the I have it already done it, but the build is done. Bin. This is the bin directory, but it's the bin directory in my own, right? It's this bin directory. Then in order to have the life easy, I will create, now forget about it, I will create here a symbolic link to the programs that I have done before. You do with ln-s, creates a symbolic link, then you have to put the name of the program that you want to link. It was robot programming 2022, source, srg2 workspaces, devel, lib, srg2 executor, srg2 shell, and we link it. And then we have it. Now if we say srg2 shell, from wherever we want, we start it. Okay. All right. This is the first program that we want to link against, and then also another program. It's in the package srg2 config visualizer, appnode editor, but it sucks the name, so I call it confvids. And we have a program here which is called confvids. Another thing you might want to do is open your tilde bash rc and tell that in the path you have to add this export, specifying that the binary should be looked where they were looked before, but also into the bin directory of your home. So in this way, if you do so, you will be able to start G2 shell from wherever you want, okay, without having to specify the path or anything. So second thing that I recommend you. Now the building is built, and how do you figure out whether the DL thingy went well? If you start as a G2 shell, you find that here you have a lot of success, like opening library, opening library, opening library, opening library, and so on. Okay. If it doesn't find the libraries, because maybe I messed up the DLconf in a weird way, which I can do somewhere, then I will get a lot of red thingies. All right. Yes, I have still time. Yeah. Okay. Where was it? There is another program which you might want to compile, which is called proc webctl. Now I think I don't know where we put it. I think you have it. You have G2 webctl. You compile it straightforwardly. You have it in your repo. You compile it with make. That's one thing. I have 1804 and you have 2004. If you have make, I have another version of it because I have an old operating like revision of the operating system, and in particular of the libweb sockets. Don't worry. I mean, you do this, and then in the end I go to my revision. I can just like download the new version from GitLab. Okay, so this is the repository from where I'm downloading, and I need the master. Master is 1804, clone, copy, close, mkdir show stuff. I can do it because I have the registered keys. Okay. There must be some evil stuff that I uploaded. Okay. And for me, it builds because it is a different revision. A library not made by us changed between revisions, and so we are paying the consequences. Okay, this is another program that we want to have. Now, once you have, what do you have installed? A lot of things, in fact. The three programs that you'll be playing with are, one is the shell, that basically implements a running environment for all the modules. The modules are defined, are loaded through dynamic libraries, and then you can do all sorts of things: start, stop, processing pipelines, attach viewers to the modules, do whatever you want. The visualizer allows you to construct pipelines. Now we will see an example. And then you have also these processing modules are built into these shared objects, into these libraries that you load with the DLconf. But if you load these modules, nothing happens. You have to compose them and to tell to one of them to start in order to run a pipeline. I was forced to implement a map server, like starting from the existing implementation, because the map server of ROS didn't implement the alpha channel. And then in order to start the map server, which is a pure ROS node outside of the SRG2 ecosystem, you have to start this string over here. And then we will now start the things one by one. Okay, we will be starting a localization system, okay, by using all the tools that are here. But actually, like, I'd like to refer to the slides as a lookup for you later, because I think it's much better that I show you what to do and I speak on the actions that I compute on the shell. Otherwise, this is just a lookup library that you have on the slides. Now, to test our things, what do we do? What will we be doing? Yes, no, ROS CD. No. We have to go to the workspace. Robot programming, source, workspace. And we have also clearly to source this workspace. We source the workspace, we are happy. Now I close a bunch of these evils, a bunch of tabs, so that I relocalize myself. Less things open, better, nicer. We go into the source directory, if I'm correct. Things. Or navigation today. All right. Now, you have all sorts of things here. This is the folder which contains a bunch of configuration files. Okay. Okay. Now, in this folder, we have stuff. In particular, we have a map, which is the map that I have shown you last time. The map of the department. Here it is, right? The map of the department. Now, we might be interested in testing the system that we have just, brought up. And the very first thing that we could do, I mean, I observed that here we have we don't have a bug file, or is there a download dataset somewhere? No, maybe. Yeah. There is this data set here that you have on top level. All right, we have this data set. Now, navigation today. Well, the very first thing that we might want to do is to start the map server. Or first we need to start the ROS core. Started. Another thing that we need to do, given that we don't have a robot, is to start a simulator. To start a simulator, we're going to use this Word file. And we have stage. Now we have stage here. I just like put it on another window because it disturbs. Now another terminal. Now we are ready to, we have the map server. How do we know that we have the map server? The map server was, this is the map server. This is the map server. Where was the map server? No, I didn't start it yet. But in order to not get stupid, let me do one thing. I can't change the name of the terminals. Yeah, I can't change the name of the terminals without being me. But we remember that here I have stage, and here I have ROS core. So ROS core, stage. The third one. No, this is not interesting. Third aspect that we are doing is that we need a map server. Well, to start the map server, we remember that we have to source the workspace. mouse. All right, and we have it. Cross run. So, and then the map comes into this YAML file. Of course, my mouse is really working well today, and it says, okay, I read the map. Now we should be able to see this map onto our vis, for which we start our vis. We start at vis, we choose top-down ortho as view because the other one, we blast the grid because it goes on my nerves. No, here, remove, and we add the map. By topic, the topic that we have now is map. Oh, we are able to see the map in our vis. Who gave the map to our vis? The map server. So we have the first component up. All right, other thing that we might want to do, now we are ready to start what? Let's see where our robot is. Our robot is in this location over here, right? And then to start our robot, we might want to start the localizer. You say, but where is the localizer here? I mean, mind your business, that would be the answer. But the localizer lives into this file over here. Because it's a pipeline, it's not really an actual binary, so I could straightforwardly visualize it. How? Again, source / robot programming devel. If you put it in your path, source /2 space devel set2 push. Okay, now I'll teach you another trick, right? Because we are bored of doing this sourcing, right? But we also don't want to have too many to have this workspace always active. So what we normally do is emacs /.bashrc. We open it and then we add an alias. But I don't remember. Help. Alias. Okay. Alias name value. Okay. We add an alias to a command. Was it here? Yes. Alias. This. Oh, yeah. The help. Oh. Alias name equals value. Very good. Workspace robot programming equals we have an alias. So each time we will write vsrp, we will source the workspace without getting stupid. All right. So conf vids what localizer 2d.conf. Then right. minus c. Yeah. All right. And this is the configuration file of the localizer. Here you see all the modules. Okay. Right. Namely, it's not dramatic what the system is doing. We have an object that requests the map, navigation to the map requestor ROS, horrible, that produces that each time it receives a map, it feeds it to a localization module, which is here. The localization module receives the transforms, sorts the messages, because sometimes the messages on the net, they are not sorted, and then operates on the topics that you give it. Here you have all the parameters, don't change them. Now the pipeline, the system works that you have a source of messages, and in this case it's the ROS source, so it listens the ROS messages, and then it writes the ROS messages into this thing. So if we want to run the pipeline, we have just like to trigger, to turn on this object, and this object will do, okay? So that's what I will be doing now, okay? This is the configuration file. Now I'm opening the configuration file with the shell, and also I will be showing you that you can do it, let's say, in an easier way. But first we'll do the complicated one. Synergy to shell. We start the shell. We open the file. local. We open. If you open the file, we can ask the file in. We can see that we have loaded all the objects we are interested in, right? And then what do we do? What do we do? Guess what? We run. What was it? Yeah, something like that. There's something more to be done, but I mean, what was it? Like actually, like we have to. This is evil, but we have to do this. We have to execute a bunch of commands. The very first command that we have to execute instances. Oh, instances. Oh, we have a thing which is called I hate this. I have to reduce the font. How to reduce the font of this evil? No. I can't see the names basically. We have a thing exec search open exec sync open instances. We have to open the tabs of the thing. Exec. There is an object which is called requestor. This is commands that I'm help. Okay, exec request, exec requestor, request map. You can control the individual objects. We started the map, and then you will see exec runner. Run. Huh? Where was it? Run runner. Second, probably I started twice the modules. Okay. Yes, I know it. The system failed because I paused the stage on the other machine. Okay, and then it says no, I can't go on. Okay, now this is an ugly sequence of commands to run, but it basically serves to show you that everything, my real program is nothing else than opening a configuration file and starting some modules one by one. You can do this if you have configured your system correctly by writing a script. Like there is this script in this directory which is called localizer2d srg that is doing nothing else than issuing these commands one after the other to the shell that you have configured. So if you want to start a localizer, you just like run this script and you have the localizer running. Having the localizer running allows you to see something on RVs, hopefully, if the system is running. Is it running? Empty model, interpolation. I know it. So MTF view frames. These are the frames. Base laser link. Okay, with order. What do we have here and why don't you work? Now we have the scan. Okay. This was the localization. Where is RVs? Yeah. Ah, I know why I don't get anything. In order to see something from the localizer, you need to add the display. And which display do you need to add? You need to add the particles. And then you need to restart the localizer because it didn't send anything. And now you see the particles in the game. So this is the hypothesis of Lobot position. Okay, that was the mistake. I didn't enable the particles on the display. If you do so, no, this is not enough goal. You could set a 2D pose estimate of the robot. But you say, how do I figure out that the position is correct? Of course, I have the simulator on the other side. Well, a good option would be to to visualize a laser. How do we visualize the laser? Laser scan over here. Of course, the selection, the default parameters are horrible because the scan is barely visible. These are these non-visible points. And so we say we want to see the laser in points, and you start seeing it already better. And then we change also color transfer intensity, flat color. And then we set a color that makes sense, like yellow, like green, blue, dark blue. Select. Okay, and now we see our fantastic laser scan. Now we would be able to drive our robot. To drive our robot, I think I need a joystick somewhere that I have. Yeah, we don't care. I don't have a joystick. We don't drive a robot. Now, to start a planner, we could do the same thing that we have done before, like starting the shell and loading the modules. I mean, if you're interested, there is convits, or we run the script. That's why I make scripts, because I don't remember all the commands. Cat planner 2d.src. So these are the commands that will be executed. You open a configuration file, you open the source, you open the sync, you recast the map, and you run the run. So planner 2d. Oh, I don't function. No, it functions. Yes, it functions. And now we have the planner running. Okay, this is not a big issue. Now that we have the planner running, we could do something interesting. We could send the robot a goal. We send the robot a goal. It receives the goal, but it doesn't start. Why doesn't the robot start? Because we have a third module that we need. How do we see that the planner is running? We can add, guess what? A thing on ROS which is called path. All right, and you can see this thin, horrible line that is the path, which is barely visible. So, but I truly, seriously, deeply hate the things which are not visible. Lines, billboards. Oh. All right, we see the path to the goal. I change the goal, I send it here, and I have a new path. Okay, this is done by, you know, communicating the things through ROS. Okay, now, like, what do you do to move this robot? Well, ideally, what happens when I send a ToonEnv goal? I send a message from this object to, RVs sends a message having a certain topic to the planner. The planner receives it, and then it recalculates the path. Okay, now it would be cool to make the robot moving, but the robot is not moving. Why isn't it moving? Because the planner just outputs a path. To execute the path, you need another module, which is still in this ecosystem, that actually starts executes, like controls the mobile base by publishing command vel and consumes the path as long as the path is digestible. And then I think we have yet another program. So there are 4 cross VSRP. Workspace robot programming, cool. ROS CD. Now I'm ROS CD. ROS run. To navigation to the ROS path follower up. Path follower path follower up. Okay, and we have that. Now I have to issue again the goal. What are the topics that I'm receiving? Path topic path. It's not receiving the path. Let's see. Echo cross top. I think I know it. No. Why aren't you working? Base link frame ID, base ID, threshold path. So this is an idiot. Cross topic echo path. Now I'm asking this is troubleshooting in ROS. I'm asking if I see a path to the nav goal. Let's go here. Let's see. No message received. But how can I see the path from this object, from RVITs, and not see the path through the stuff? To the nav goal, I send the robot here, and I see a path, and I don't see a path if I do this. Isn't it funny? To the nav goal, go here. I receive a path, but this guy doesn't digest the path. Why? Echo path. Cross topic list. Okay. But it stays running. Okay. I don't understand this. We have the planner running. Where was it? This is the localizer. It was nothing. Okay. Here we have ROS core. Here we have stage. Here we have the map server. Here we have the localizer. Here we have the. Now here we have RVs. Here we have the localizer. You know that I think I killed the planner? No. Oh, did I kill the planner? Let's see. I killed the planner. I probably typed Control C somewhere. That was the reason. Started the planner. Now, yeah. Now it works. Okay. I killed the planner in one of my Control C things. ROS run. search to navigation to the PS RP source the workspace ROS run G2 navigation to the ROS path follower app. Oh, finally the robot is moving. Okay. Now what happens? It seems complicated, but I mean, once you have the configuration ready, and of course this is not how I start navigation, because now you have the new program that allows you to start all this ecosystem in an easy way. Oh, now we are able to send the robot wherever we want. Oh, we want to send it here. Now I think it's following the path, and therefore it will bump into this box. Here there is a fantastic box, and it will horrendously bump into it. Let's see. You see that it's planning the path around, but it was following a different path, because we have two paths which are output by the planner. One which is the global path, the green one, and the other path that is the nice one that is not visible because the style should be thin lines and not billboards. Which didn't implement, basically didn't follow the right thing. Now I move the box. You see that there is a box, you see that the robot is nicely planning around, but it's following the wrong path because there are two paths generated. One which is called local path, which is the good one, and the other one is the global path. So now, how to fix the problem? It's quite simple. I could simply say that this object here, has to read the path instead of from this topic, path topic, I think it's called local path. Okay, now let's see if it works better. Of course, I have to depossess to the nav goal. Okay. But did I select the correct local path? No, it's still path, this idiot. Path topic. Okay. Like I put one more underscore. Okay, now you see that it avoids the obstacle. I'm playing with the obstacle. Perhaps you want to see this. I'm playing with the obstacle. Okay, yeah, well, that the goal was there. To the nav goal, let's send it here. And the robot decides that to go here, it's much better to turn on the other direction. Okay, you have navigation running, but this is horrible the way to start it, and this is actually not what I do when I start navigation, and there is a better thing you can do, which is technically run using the fantastic WebCTL program, okay? So if you put your WebCTL program, now I will close all these obscene things, all of them, and I will show you how you can start all the infrastructure trivially. Because this is actually what I'd like you to do. Control D, Control D. There is a fantastic program here, a script here. Let's open it. Emacs run navigation WebCTL. Here it is. Now, well, this is to make it horrendously generic, but doesn't change much. This program, this object over here, creates an alias for a string and a command. Okay? Okay, this is just expansion variables. Opt ROS, this is to be compatible with multiple ROS distributions and whatever. But in the end, what you see is that it's doing nothing else than the commands that I started from the shell. Okay. Now, if I start this web control, passing it this program, I have a thing which is fantastic. ROS proc WebCTL run navigation WebCTL. Nothing happened, right? It's not really true because there is something else that happened. On my machine, localhost to the port 9001, I have web server running with which I can start the programs without becoming stupid because I prepared already all the scripts. So let's start the core, let's start stage, let's start the map server. That does nothing. Let's start RVs. Let's configure this thing. Delete the grid. Add map. Okay. Map. Did I start the map server? Where are you? Boo. Map server. Start. Image capture laser diagram. Okay. Well, not cooperative, eh? Color scheme map. Map. Topic. It wants to have a topic. Yeah. And now how do I interact? Panels. It wants to have a topic for status 1. No map received. Control C. Start. Yeah. Today this machine is not cooperative, eh? Did I have another map server running? Or maybe the map was not sent? No, sending map. It's here. Guys, today I'm not lucky. And by topic, map. It received it. Simply the zooming factor was wrong. Control C, start. Let's start again. Do I have it? Okay. I do it, I blast this and blast this because I want the process to be repeatable. I start the map server. I start RVs. I add the map. Oh, it worked. Non-deterministic orbits, top-down ortho, yeah, of course. Okay. The map is here. Then the stage, I blast it, I minimize it. I start the localizer. But of course here you have to select the particles if I want to see something of the localizer, right? Start the localizer. Oh, I see the particles. I set the pose estimate more or less where the robot is. Shall it be here? Of course, I need to modify the evil. You can save the stuff. I could say you can save the configuration. I add the laser scan. Of course, you have to change the configuration and to make it visible, right? Okay. And file, save config. Yes, save it. Replace it. I don't care. You don't want to save it. File. File. Save config as home. Why? Save it there. All right. Another thing that we want to do is to start the planner. And then we are done. Then we have the path follower, which was the last command that I started. And yeah, there's not much. Of course, we need to add all the displays. It's like more like a GUI. That's why you find me so handicapped. Billboards. Billboards. Okay. And by topic, particle, local path. Again, billboards. billboards. Change the color to something that sucks less. Okay. And then the robot moves. Observe that it was delocalized, but slowly it will try to relocalize. This is quite an interesting thing, because you see that the particles distributed in two groups, but at the end one of the two hypotheses has won to the enough goal. Now you are able to drive your robot. Okay, that was the last thing. Yeah, I know that I went long, but I don't care. That was the last thing that I'm interested in showing you, and it is how to build a map. No, I will show it to you next time, and we will do a wrap up. So basically what you have today installed is an entire navigation system that you can play with. And there is this convenient, really convenient web interface that prevents you from remembering commands, okay? Safe. No, probably I went too long. And I think I've lost also the web. All right. So now next time I'll show you how to watch a map, and then I think we are a little bit over time. So next time will also be the last lesson. Okay. But actually, if you want to build a map, I think you can do it directly on the web Morte web server. Where was the web server? Huh? No, wait. Ah, here. You can also do it. I think. Well, building a map is easy, and I think it was in the Slum today. Slum today. .srg, and then you give it a file name, and then of course you have to start the evil raw score. What was it? The bag is not here. Of course, my mouse. Okay, this is how to build a map. There is another script. It's processing the bag file and it's producing the map. Of course, I've given you also the file of the run that I recorded in the class. Once you have done, once this program is finished running, quit. How to get a map is quite easy. You just like mi mape. You call this script and then you write the name of the map that you want to generate. Does all what it has to do, generating a map. This was the department, but you have it. You can have it also like in different forms or from different environments. Once it has done, okay, quit. Let's see, mi mape, eog, mi mape, and this is the map. Of course, there are tools for rotating it and doing whatever you want. So, where is the script? You can see it, it's here. Clearly, once you run it on a different bag, you will have to adjust some parameters or some file names, for instance, and topics and whatsoever. Have fun. Ciao, guys.